Hello, everyone. There will be a theoretical part where I show slides and a hands-on that allows you to publish your collection data or your observation data to GBIF and to other networks. The idea is to show how you do it in the IPT and then do it on your own with the test data. And then the next part, and hopefully at the end, everyone will have a small data set published to the test site of GBIF. And you should be able to do that later again with your own data. If you feel very brave, you can do it with your own data set. You just have to make sure that it's in the same format as the test data set. That is 2 or 3 CSV files that we can connect to the IPT, and then do the mapping between the standard and your columns, and then it should work. I'd recommend to do it with a test data set so that you can really follow the stuff I'm showing, and then later you shouldn't be a problem to do it on your own. So first, what is GBIF and those biodiversity networks about? It's what we call primary biodiversity data. It's everything that documents the existence of an organism at a specific location at a given time. And the organism can be identified as a species or on a higher taxon level. Of course, the location and time will be designated by time and coordinates and locality description. If we have something like a vegetation plot that tried to identify all the organisms in a square meter, for example, you can also record absence data, the absence of a list of taxa in this given area. This is also considered a primary biodiversity data. In short, primary biodiversity data consists of 4 areas of information. What is documented, where was it documented, when, and by whom. So either when it's a specimen who collected it or an observation who observed the organism. And as a short term, we call that occurrence data, and that includes absence data. So if we look on GBIF, we'll find most of the data is occurrence data documenting the occurrence of something, but there will also be absence data, but that's included in the term occurrence records. So where do these information come from? Since I'm from the Botanic Museum, of course, the first thing that comes to my mind are the natural history collections, the herbaria. In Berlin, we have about 4 million herbarium sheets. Herbarium sheet is a dried plant mounted on a cardboard, attached with a label where all these information are recorded, who collected the specimen, where, and who identified the specimen. It is estimated that in herbaria worldwide, there are about 400 million herbarium specimens, and most of them are not on display as in usual natural history museums. In Berlin, they're stored in an underground vault and usually just accessible to scientists. You can see the label. Often, if it's a historical specimen, they're handwritten, so it's pretty difficult to identify them, to identify their handwriting. But with newer ones, it's typed or printed labels. As with most collections, the herbarium in Berlin is growing. It's about 30 or 40,000 specimens per year that are added to the collection. It's a constant growing set of specimens of biodiversity data. Of course, we have also all the other specimens in natural history collections, all the pinned insects, the stuffed animals, the animals in alcohol, the vet collections, the small insects just contained in vials. And when it comes to general natural history collection specimens, the estimate of numbers get a bit weak. There are estimates that there are about 3 billion specimens. Some go up to 10 billion. And as with the herbarium collections, only a small percentage is on display. I think the Museum für Naturkunde has about 1% or less than 1% of the objects on display. Everything else is stowed away in storage. Another valuable source of primary biodiversity data are all the observations. The traditional observation databases that are collected or recorded by biologists in events like fish monitoring, in vegetation surveys, in insect monitoring, where Biologists set up traps and see which insects end up in the traps and identify them and collect them as specimens. And as opposed to natural history collections, this sort of source also is able to provide absence data. So natural history collections, traditional collections can just provide occurrence data, which specimen was collected on which site, but they cannot provide absence data because just because someone is missing in a collection doesn't mean it wasn't there. But if you do observations based on a defined protocol, at the end you can say that this list of taxa wasn't existent at this location. So you can record absence data. With the rise of the smartphones, increasingly important are the citizen science observation databases like eBird or iNaturalist. They usually come with an app that allow you to take an image and upload the data or the image along with the metadata to the project website. And often there's something like an automated identification mechanism. So the app gives you suggestions on what you observed in nature, whether it was a bird or a plant. And these suggestions are usually very good. And that's not because the pattern matching is so good, but because they combine pattern matching with statistics. The app always knows where you are exactly, at which time of the year, and at which time of the day. So they combine statistics on what can be found at this location, usually with the image you send. This intersection of both yields pretty good results. Identification results of these apps are very useful. And usually you can straight away upload your image and your observation to the platform. And other citizen scientists can have a look and identify the organism you observed. Unless it's a very rare organism, usually within hours, there will be someone confirming your identification or, well, correcting it if it's not correct. For example, iNaturalist right now has about 300 million observations they share with GBIF, and eBird is even bigger. I think right now they have 1.8 billion bird occurrences. That's because everyone loves birds, and with the app, it's very easy to record them and to upload them. So we have basically these two large types of sources of primary biodiversity records. It's the observations from traditional observation databases and from citizen science projects, and the old natural history collections with their specimens. The advantage of the observation databases is that the information are already available in a digital format. So they are in a database and you don't have to put in any energy to get them. That's different with the natural history collections. As I told you, there is a huge amount of specimens hidden in the collections. And the first step to make them available is, of course, to digitize the specimen. That's easier for herbarium specimens since they're flat. And the image on the top is how this is done in the Botanic Museum. The specimen is put into a scanner, and then the image is taken of the organism and the label. And this is done one by one with manual handling. So, of course, this takes a long time. The image at the bottom shows how this was done in the Herbarium Paris. 10 years ago, they got the funding to completely digitize their herbarium, and they shipped away all the herbarium specimens to something like a warehouse where they had conveyor belts and everything was done automatically. This was mass digitization, and they were able to digitize all the 5 million specimens and take the images. And that's something that should be or is planned or is aimed at for German herbaria, but hasn't been done so far because of lack of funding, as always. If you look at the labels, these are historical specimens, and you can see that it's not easy to read them because it's old handwriting, and often only part of the information is recorded. So you have to have a lot of knowledge about the collector or the expedition to be able to decipher what exactly that's meaning. The process of digitizing the specimen is only a first step in making this information available. The second step is the metadata capture from the labels. In the very past, it was largely based on pattern recognition. Algorithms were developed that aimed at identifying labels and then OCR on these labels with results that were not very good. The reasons were that partly the handwriting is very difficult to decipher and that the information written on the label is patchy. So a very new approach to capturing metadata from digitized specimens in herbarium labels is based on crowdsourcing. That is to try to involve people, volunteers in the process of transcribing those labels. And the trick is, as always, to include elements of gamification. One of the projects that was very successful in Berlin and in Paris is the Herbonauten, which included elements of gamification and of competition into this game. They tried to combine specimens in missions and they put it on the website and people could register and then try to transcribe those labels. And by including this element of competition, it was really amazing how eager people were to transcribe more data and to be better than each other. This is the list of the top herbonauts in Berlin, and you can see that some of them did 300,000 contributions. So they transcribed 380,000 locality texts or identification results, scientific names. That's quite a lot. And this is how the Herbonauts website looks like. On the right, you have those specimens to be transcribed, and on the left, you have an entry form for all the elements of the labels, and people look at the labels and put into the forms the elements they can find. And again, on the right, people have to be very good at transcribing or deciphering old language on old handwriting. And by the time people became experts on the handwriting of certain collectors. And they even started to have their discussions on certain collectors that were considered different persons. Altogether, there's been 2.5 million contributions. The contribution is an individual data item. Someone transcribed 160,000 specimens. That's more than all the employees of BGBM transcribed before. That's a lot. And they've been grouped in 50 emissions. So emission is always something on a specific collector, on a certain geographic region that makes it manageable. Emission can be completed within weeks. Usually, two people get the same label, and if they both enter the same fact, then it's considered right. There are newer approaches. One is AI, and this is surprisingly good. So I tried to transcribe the specimen on the left with ChatGPT, and it was able to extract what we see on the right, which is really good. If you see how difficult this is written or how bad the handwriting is and how patchy it is, the problem with AI you can find here is hallucinations. The things I marked in right are not written on the specimen. So these are words that usually come with other words that the AI hallucinated and added. That's a thing that has to be solved because you can't have text and descriptions that are not on the label. That's worse than having less than it's originally on the label. We have these different types of occurrence records and where they are stored. If you started putting everything in a database like 30 years ago, you had to do your own hand-tailored database. For example, at the museum in Berlin, we have our own SQL Server database that was developed like 30 years ago because there were no collection management systems by then. Nowadays, there are off-the-shelf collection management systems that you can use, or there are consortia of different institutions who decided to create their joint collection management system. For example, JAC is for herbaria. About 30 herbaria in Germany use JAC to record specimens. And the question is, how do the data or the occurrence records come from these collection databases to networks like GBIF. If it's an off-the-shelf collection management system or something that has been developed by a consortium, it's pretty easy because they have APIs and export options to get the data out. But with the hand-tailored databases, it gets a bit difficult. And that's where tools like the IPT come into place. First, a basic principle of biodiversity or primarily of occurrence databases of those networks is that the records stay in the database system where it's recorded. Because usually these are living databases, so people work with that. They regularly enter new records, they correct data, they newly identify records. It's not a good idea to export data, put it on a USB stick and send it to a network. The idea is that the data remains in the system where it is. Curators continue to work and to enter new data, correct the data, and the networks index, re-index, they drop by every week and record any changes and load new data from the databases, but the data remains where it is. The advantage of this idea is that the curators, the data owners remain in full control, so they can always decide not to publish any records, so they can remove records that maybe they want to do a publication on some research first, or they can hide certain information items like the exact location of an endangered species so that no one can misuse that data. That's something that always can be done by the curator because they remain in full control of the data. And that's the same for all these data networks like GBIF, GGBN. One thing that has to be agreed upon is, data standards, ABCD. That's a community standard for natural history collections. And it has a defined structure, how the data will be structured, and a set of data items or fields where to put the data, and the family, the recording date, the collector person has its place in this data format and will be stored in one of the data fields. So all the information items on the website will be stored in the data standard, in this case, ABCD. And by using this data standard, it's very easy to access this data by networks like GBIF because they don't have to deal with the peculiarities of the collection database or the observation database. So all they have to know is where to find a certain information item in ABCD, and it's completely unknown to the network where, in which database this was originally stored, in which table and in which column. The networks just understand the data standard, and that's enough. Historically, there have been two competing standards in the primary biodiversity data community. One is ABCD, access to biological collections data, that originated in the natural history collections community. Another one is Darwin Core, which was based in the United States. And since they have different origins, they differ considerably. ABCD is very complex and very comprehensive because it's from the collection community, and you have a lot of different types of collections with very peculiar data items they want to store. So ABCD is very comprehensive. The latest version of the standard has about 900 elements, which is really scary. Whereas Darwin Core is rather simple. The first version had about 40 elements, and the latest version now has about 150 elements. Whereas ABCD tried to include everything, Darwin Core was kept simple, and for specific use cases, it can be extended with additional fields. ABCD is XML-based, so it's always in the XML text format, whereas Darwin Core is just a set of terms, and it can be put in any serialization format you want. So it can be XML, it can be JSON, it can be CSV, it can be RDF, whatever you want. Of course, the standard is not enough because you have to provide tools for the data owners to convert the data into this data standard. You already heard about BioCase. That's a tool that implements the ABCD standard. So you can install BioCase next to your collection database and connect it, and then map the elements of this ABCD standard to your collection database. BioCase will convert your specimen records, your observation records into this ABCD format. For Darwin Core, GBIF developed the Integrated Publishing Toolkit, IPT, which is very similar to BioCase. It can also connect to a local database, but in addition, it can deal with uploaded text files in Excel and spreadsheet files. So this allows to use this also as a cloud installation. So BioCase is something that needs to be installed in your institution next to the collection database, to your herbarium database, for example. Darwin Core, you can do the same, install it on your own servers, but also use it as a cloud installation offered by GBIF, for example. BioCase and ABCD are used extensively in Germany, and for example, all the 7 natural history data centers of GF Bio rely on BioCase and ABCD. GBIF, the idea is to provide free and open access to biodiversity data, to support policymaking, to support researchers. GBIF offers access to 3.5 billion occurrence records. Most of them are observations. And these data are drawn from over 100,000 data sets. And they differ very much in sizes. The smallest data set, I looked it up, has 12 specimen records, and the largest data set is eBird with 1.8 billion bird observations. That's half of the records in GBIF. There is a strong bias towards observation data in GBIF from citizen science projects. Half of the data is from eBird. So if you look at the taxonomic metric, you can see that 2/3 of the records in GBIF are on birds. That's why some people are joking that GBIF is not Global Biodiversity Information Facility, but Global Bird Information Facility. There is a huge gap in information. If you look at the number of occurrences, it doesn't match the number of species richness. That's something that has to be tackled, and GBIF is trying to do, but with the rise of those citizen science projects, this will probably get worse. On the top left, most are human observations. I think that's 5/6 of the data are human observations, and the preserved specimens, the natural history collections, they are getting a smaller percentage over the time. GBIF is funded by the voting participants. I think 48 voting participants right now and associate participants. The data on GBIF can be accessed in different ways. You probably all used the data portal where you can easily set filters on all the data items of occurrences. And once you've found your occurrences of interest, you can download them as a CSV file, either as a plain CSV file or Darwin Core archive. And with those downloads, you can continue to do any processing. You can, for example, use it in an R script or in a Python script and do your own processing and transformation. There is also a REST API. Actually, all the data portals that offer GBIF data are based on this API. So all the information you can access in one of the portals, you can access using the REST API. And if the language of your choice is Python and R, you don't even have to create your own API calls. You can just use one of the packages that GBIF offers, for example, PyGBIF. And if you're familiar with Python, these are just 2 statements to access occurrence data in a Python script. So it's very easy if you use Python or R to access GBIF data. And it's the same information you will get through the REST API or the data portals. SQL downloads. If you want to process or if you want to do analysis on a lot of GBIF occurrences, and you want to do this through a regular download, you would need to download huge amounts of data. which will be a huge download file, a huge core archive file or text file if you extract it. Then you'd need to import that into your own database or R to do your analysis. And the SQL downloads allow you to do SQL-like analysis on the occurrence data without downloading them first. The statement you see here, it looks like SQL. It has not all the features of a regular SQL database, but it allows you to do aggregations on all of the GBIF occurrences and download just the few numbers you really want to do. So you can use aggregate functions like min, max, count, average to group data, or to group the data into categories, and to aggregation functions and do calculation, and just download a very small data set of numbers that you're really interested in. If you combine SQL downloads with occurrence cubes, it gets even more powerful. If you want to do temporal analysis on occurrence data, or geographic analysis, or taxonomic split ups on analysis of data, you should have a look at species occurrence cubes. They're a very powerful way of running analysis on GBIF occurrences without downloading a whole amount of records. Something that GBIF offers are the GBIF portals. It's an easy way to set up your own data portal for GBIF mediated data with a subset of records. So you can set up your own filter on, for example, some geographic region or some taxonomic group or whatever filter you like, and create a portal without doing any programming skills, just with markup files, and then offer your own portal. For example, we created the virtual herbarium. Currently, there are about 25 herbaria accessible through this website, and it allows access to about 1 million herbarium specimens, which makes it way easier to find information. So if you're looking on the GBIF data portal, you have those 3.5 billion records. And if you have one of those hosted portals, it's easier for a community to find specimens of interest. So for botanists, this virtual herbarium makes it easier to find the specimens in the area they can work with. There's another hosted portal for NFDI biodiversity. It's the land portal. This focuses on German biodiversity, currently about 65 million occurrence records. And the idea was to just offer a subset of the GBIF data and not to drown people in data, and to mobilize more data, to put some gentle pressure on data curators to publish their data to GBIF. If you have like 3.5 billion records in GBIF, it doesn't matter if your own data is added to this huge pool of data. But if it's a smaller subset, like in the land portal, some curators or data owners, they look at the portal and they see my data can't be found there, and they by this way get nudged a bit to publish their data also to GBIF, because with this small portal, it becomes more visible. What's in for the data providers? Of course, first thing, everyone loves you because you publish your data and you make your data available to everyone, and it becomes easier for curators to work with your data. If it's specimens, they don't have to request loans for specimens. They don't have to travel to the specimen, to the collection site, and they can draw data from a lot of databases and analyze them and do research without any effort. But we all know that love doesn't pay the rent, and the currency in research is papers and citations. And that's why GBIF supports citations of data sets, of data in scientific papers. If a researcher uses GBIF to draw data for research, he or she will use the portal to find those records and then create a download to continue processing of the data and to do analysis. And for each download, GBIF issues a DOI. And this DOI is something you will use in your publication. So if you use GBIF mediated data in a paper, you will cite this DOI, and GBIF is tracking this DOI in a huge list of scientific publications. And whenever this DOI is cited, it is recorded. And if you look at the data set, in this case, it's a variant data set, GBIF will list all the citations or all the papers that used data from this data set by using this DOI of the download. So in this case, there have been 307 papers with data from the variant trace tensor, and these are all papers that use such a DOI in the download. And of course, GBIF records all these papers. You can look at the list of the papers and even watch them or download them. So GBIF helps you to publish papers about your data. So you all know data papers. That's a publication about the data set, not about research, but just about data that has been compiled. And if you use the IPT, for example, to publish your data to GBIF, GBIF has developed a workflow that easily allows you to create a data paper from this. Once you've used the IPT to publish your data, creating such a data paper is a no-brainer. It's a very easy thing. What benefit do they have from publishing their data to GBIF? One thing is credit. This is the website on GBIF for the Botanic Museum. The Botanic Museum has a lot of data sets published to GBIF, more than 55 data sets, most of them with natural history specimens. And that's an overview that GBIF creates for spanning all these data sets. So we've published different data sets from the barium, then the lichen herbarium. We have some observations, and these data sets are in isolated databases, and we wouldn't have any overview of what's in them. But by publishing data to GBIF, you get a very good overview of what's in all the databases. So all the numbers you see, the occurrence map, then the taxonomic breakout on the right, and the temporal split up, this is done over all data sets. So publishing your data to GBIF gives you a good overview of all the occurrence records you do have in your collection databases. The IPT is one of the tools you can use to publish your data. It uses the Darwin Core data standard, and it's used by a lot of installations worldwide. Probably over 70% of the institutions publishing data to GBIF use that. Other ways of publishing your data to GBIF is either to create your own Darwin Core archive, or you can use BioCase as well. As I mentioned, the IPT can connect to relational databases to draw the data and to convert it into Darwin Core archives, but also can upload tabular data from CSV files. Now, I mentioned Darwin Core, which is the data standard used by the IPT. The Darwin Core archives are a way of serializing Darwin Core data. That is to put a set of Darwin Core records into files and to send it over network to GBIF. The Darwin Core archive is basically a zip file which contains several text files, CSV files, and two metadata description XML files. In the CSV files, there's one core file which just has the Darwin Core terms. As I said, Darwin Core is rather small, and it concentrates on these four basic data items: what, where, when, and by whom. And these are the occurrence information we have. These are contained in a CSV file in the core file. If you have additional information that cannot be contained in the core file, you have to use an extension and put into one of the extension files. And the Darwin Core archive uses the star schema. In the center, there's always the occurrence record, and each occurrence record can have up to many entries in one of the extension files. For example, you have one specimen that is in the core file, and you want to provide several images for each specimen. So you would use an extension for these images. And in the file for these images, each specimen would have, for example, 4 images. If a specimen had 4 images, there would be 4 rows in the extension files. You could have another extension, for example, historic identifications. So for specimens, it's often very usual that you have one current identification, which is the current scientific name for a specimen, and you have the historic identifications with old names that you want to provide. In the core file, there would be one specimen, one occurrence for the specimen with the current identification, and in the extension file for the identification, there would be maybe 3 rows with a hit for each historic identification. This is the data part in the CSV files. Together in the Darwin Core Archive, there are 2 XML files describing the data set. One is in the EML format, which is ecological markup language, and that's the metadata that describes the whole data set. That is the title of the data set, a short description of the coverage, so which taxa are in the data set, which geographic regions are covered, the contact persons, who owns the data, who collected the data, and who should be contacted in case of questions. All this type of metadata information are contained in the metadata file eml.xml, and the meta.xml describes which files are in the zip archive, which is in the core file, what's the name of the core file, what's the CSV dialect in the core file, which extensions are used, and which columns are in the extension files. And all these data files zip together with the XML files. They form a zip file that is called a Darwin Core Archive, and GBIF can download this file, index the data, and view the records in the data portal. Well, let's have a look at the test data set we will use. It's taken from a course offered by GBIF on data mobilization, and the data was drawn from historic literature in Denmark, where bird sightings near Danish lighthouses were recorded. So the whole process of digitizing the original literature, extracting the information from the literature, describing the occurrences, the observations, then data cleaning and publishing to GBIF. In this course, we will just do the last part, the data publishing. We start with files describing these bird observations, and we want to publish them to GBIF. Look at this test data set. It contains 3 files. One is the core file with the observations of the birds, and 2 extension files. One contains the links to the original literature, to the PDFs of the scanned books, and the other one contained the historic identifications that are old, that are not current, but nevertheless, that's useful information that was recorded, and we want to publish that to GBIF as well. If you had a look at the files, they are regular CSV files. You can have a look at them in a text editor. You can open up in a spreadsheet application. So you have different columns separated by the tab character, and each line contains one observation of a bird. What makes it very easy for us now is that the column names are already named after the Darwin Core elements. You will see later that it's very easy now to map this data set to the Darwin Core data standard because the terms are the same. If you have your own data set, that probably wouldn't be the case. So as part of the mapping later, you would need to translate or create a mapping between the Darwin Core term, for example, for the scientific name, and the column in your data set that contains the scientific name. As I mentioned before, you don't have to install the IPT on your own servers. You can use it as a cloud installation, and that's what we will do now. So we won't have to deal with the installation of the IPT. That's something you would need to do if you want to have your own installation on your own institutional servers. But the first thing you'd need to do is to install BioCase. Then what we will do is first create a resource. A resource is the term in the IPT for a data set. So all the records, all the observations in one resource will be observations in one data set on GBIF later. Then another step is to upload your data. So if you have your own installation in your institution, you can connect it to your collection or observation database. In our case, if it's a cloud IPT, we will upload the source data. That is these 3 text files we do have. In the next step, we will create the mapping between the data standard and our source data for the core. Then in another step, we will do the same for the extensions. Then we will enter the metadata. That's all the information I mentioned about the data set, title, contact persons, iSense, taxonomic coverage. And then we will publish the source and hopefully be able to watch it on the GBIF data portal.